All right, hi everyone. Sorry for the technical difficulties. My name is Richard Young, and I work for IBM Research. And today I'm going to be talking to you about machine learning in the browser. So this is going to be targeted quite a lot at software development. So if you are already an expert at machine learning, this is probably going to be quite an introductory talk. And I hope that by the end of this, everyone here would be able to start using machine learning in their own applications if they want to. All right, so if you have any questions, feel free to stop me. It's going to be quite a casual presentation. But let's get started. So what do we mean when we talk about machine learning? So the term machine learning was originally coined by somebody named Arthur Samuel in 1959. And interestingly, he actually worked at IBM at the time that he was doing this. And he says that machine learning gives computers the ability to learn without being explicitly programmed. So what does that mean? Pretty much means that instead of us writing an explicit set of if statements, for loops, algorithms to do things like sorting arrays and doing things, we're going to write code in such a way that it's easy for it to learn given a bunch of examples that we've given to it. And we then take this thing that we've taught, we give it something that it hasn't seen before, and it should be able to make predictions off of that. All right, so how do we teach a machine? Well, let's assume we've got something called a model. And don't worry too much about what goes on inside that model. Just know that that's a terminology that people tend to use. And we want to train this thing. And you train it pretty much the same way as you would teach a person to do something. You give it a bunch of examples and you tell it what those things are. So we want to teach a model what a cat looks like. We give it a bunch of cat pictures and we tell it that these are cats. We also give it a bunch of negative examples. So we can give it a dog and say this is not a cat. We need to do this with quite a few different examples because we need to cater for every possible cat that we could encounter. So usually this is thousands, hundreds of thousands of images that you would give to your model. Then what we want to be able to do, once this model is already trained, so we want to take it into a new situation, give it an image that it hasn't seen before, and it should be able to give us some kind of a prediction. It should be able to say, is this a cat or not? So there's two distinct parts to this. You can see the left-hand side is the training part. The right-hand side has got many names. They call it inference or classification or prediction. All right, so that sounds really great. What would you as a developer actually use this for? So you could use it for identifying the object in the image, like the previous slide. Is that a cat or is it not a cat? You can use it for finding the location of an object in an image. So usually what would happen is it's not like just one cat inside the image. It's maybe the cat is in one corner of the image and you want to find where the cat is in the image. This is particularly useful for like video feeds or like security cameras and things like that. Natural language processing. So that's NLP like chatbots, understanding written commands, things like that. Recognizing and generating sounds and speech. So this is how your Google Home and Alexa would work. And where all of the money is, forecasting structured and tabular data. So given the last 10 years financials for a company, can we predict what the next year's financials are going to look like? And this is where a lot of data scientists work. So what do you need to get started with machine learning? If you Google this, you will find answers like you're going to need lots of hardware. So very often people will use graphics cards for machine learning because it's got quite intense algorithms that work really well in parallel. And it turns out that graphics cards are really good at doing algorithms in parallel. So this NVIDIA Tesla K80, you can't really see the text there, is a really good card. And you can see that it's $1,700 plus $120 shipping if you want it in South Africa. Quite expensive. You need lots of data. So some of the best models are trained on terabytes worth of data, millions of images. And when you're training that much data, it doesn't matter how many graphics cards you have, it's going to take time. often they can take weeks or months to train, which is really frustrating for the people training it because you can only get feedback as to whether it trained correctly once it's done. And of course, things will tell you to start with lots of knowledge on how neural networks work. Go do a machine learning Coursera course. You need to know linear algebra before you get started. And if you're developing your own models, then maybe you do need some of these things. But if you think about common libraries that you use on the internet, things like React and Angular, you don't need to have any kind of knowledge on how the library works to be able to use it. You can just go to the homepage, find like the tutorial on how to do it, and in like a couple of lines of code, you can start using the library. So it turns out you can kind of do the same thing with machine learning models. So all you really need is about 14 lines of HTML and JavaScript. So what I have over here is a very minimal example of classifying an image using something called tensorflow.js. And let me show you quickly what this looks like. All right, so we have an image of a cat, because we seem to be cat-themed. And what it did is it downloaded the model, and it then classified it for us. And it says that it is a tabby cat. So let's take a look at the code for that quickly. Is that visible to everyone? Can make it a bit bigger. So the first thing that we're doing, and I'm not using NPM or any other libraries, I'm using script tags for this just to make it easy, but you can of course install these things using NPM. I'm importing something called tensorflow.js, TF.js. And what tensorflow.js is a JavaScript implementation of a library written by Google called TensorFlow. And TensorFlow is written in Python, and it's designed specifically for machine learning and linear algebra. So if you go and look for an example on how to get started with TensorFlow, you're going to find some very mathematical things there. It's not going to be really easy to figure out what to do. One thing that's interesting about how TensorFlow works is TensorFlow, the Python implementation, uses a library called CUDA, which was written by NVIDIA to run stuff on graphics cards. TensorFlow.js can make use of WebGL to run stuff on graphics cards. CUDA only works with NVIDIA graphics cards. WebGL works with any graphics card. So what you end up with is something that can work on far more devices than what the Python implementation can. The next thing that I'm doing is importing something called MobileNet from the TensorFlow models namespace. And this is a pre-trained model. So remember how I told you that it takes lots of data and time and hardware to train a model? Someone else that has those things has already done that, and they've published this model for us to just use. So MobileNet is a particular type of model. There's a number of research papers that were written on it, and it's got a number of different things that it can recognize. It's got 1,000 different classes in it, so this is the source code of the classes. About 500 of these are animals, and the other 500 are just random objects that you might find lying around your house. Just an example of what some of the images look like. So this is the data set for ballpoint pens. So you can see it's quite a wide variety of images. Some of them don't even really look like they fit. I mean, this one, for example, has got a number of things in there. There's not just a ballpoint pen, there's a bunch of other things. But there's enough images that what it's been trained on should kind of hopefully maybe be able to pick up what we're talking about, which is a ballpoint pen. All right, so what we've got is an image tag. We've set the source attribute to a cat that I've just pulled from Wikipedia. Hopefully it hasn't been replaced by a cat wearing a North Face backpack. And below that, I've got an H1 description, where I'm just going to output what the description is once it's classified the image. Inside our JavaScript, Over here, once the image is loaded, we're going to call a function, and we can then call MobileNet.load. What this will do is if the model has not been initialized yet, it'll go and fetch the model from the internet, and it will initialize it. This could take a couple of seconds, especially if you've got a slow internet connection. I think this model is a couple of megabytes big, so it's important to remember that when you are putting this into your websites. You don't want to just have this thing load when people are first visiting your website. And once it's loaded, we can then make predictions. We only have to load it once, and we can do as many predictions as we want. So we can then call model.classify, and we can pass it the image element. We don't have to worry about getting the image out of it or converting it to something it understands. It understands HTML elements. We can just give it the image element directly. And that gives us back an array of predictions. And you can see that I'm logging them out here. So I want to show you what that looks like. All right, so these are the predictions that we got. There's 3 of them. The first one is the one that I printed out, tabby cat. Then we've got tiger cat. And lastly, we have safety pin. Okay, so the first 2 kind of make sense. We're like, okay, that's still got cat in the name, but where does safety pin come from? So something that's very important that it also returns to us is a probability score. And probability is a number between 0 and 1, where it kind of tells us how sure it is that this is the thing in the image. So we can see the first one, a probability of 0.8 is about 80%. So it's 80% sure it's a tabby cat. And the second one is only 5.9%. And the last one is only 3%. We can see there's a very big difference between the probability scores there. And what it's actually doing is returning the top 3 probability scores to us. So even if the second 2 are very low probability, it's just going to return them to us anyway. And we're not really sure where the safety pin thing comes from. We trained it on a bunch of images. Maybe there was a number of safety pins inside the cat images when it was trained. We can't really tell what's going on too easily inside the model.
Is there any way of telling? So can you figure out why it came up with safety pin at any stage?
So there's quite a lot of people that are doing research into that. So transparency inside AI is quite a big topic. I can't do that right now with this model, but you pretty much have to build it in at training time. And people are researching it because this isn't a big problem, but when you're using it, especially on people, you can have biases built in. So they're using that as a way to try and figure out how these biases are getting built in to try and not bias towards one particular group of people or not. But yeah, go Google transparency in AIs is a good thing to read up further on that topic. Okay, so the first prediction will always be the one with the highest value. Just going to set that inside the H1 so that we can see what it is. So one of the really cool things about doing AI on the edge, as they call it, or in the browser, is that we're really close to the sensors. So this is all happening on the browser, just to clarify. We're not sending this off to any web service or anything. It's happening on this computer. And because it's happening inside the Chrome browser, this could work on a mobile phone as well. But being close to the sensors means that we don't have any sort of network latency. And by sensors, I mean things like webcams, microphones, accelerometers, things like that. And what that means is we can do classifications on images from a webcam without any latency sending it to a server. So I'll show you another example where I'm using the same MobileNet model, but instead of using a predefined image, I'm going to just use the stream from the webcam. All right. So I tested this earlier. The lighting in here is not great, but we'll see what kind of results we get. I can make that a bit bigger, actually. Okay. Not sure. Let's see if it picks up any of these things. Can I turn this off? All right, so what I did test was if I add a bit more light, it tends to work better. Okay, coffee mug, water jug. Maybe, maybe not. So like I said, there's not too many things inside the... almost had it. All right, so it's picking up some weird things. It did work better when there was more light, but that's not too important. Anyway, so it's picking up a number of different things from the webcam. I actually want to go and look and see what images they used for spiderweb, because it could be quite interesting. If we point it there, not sure. All right. So let's look at the code for that and see how is it different to the previous example. So I'm still importing tensorflow.js. I'm importing MobileNet. And I've just got a helper script that helps me set up the webcam stuff. There's a lot of boilerplate around that, but there's nothing special in there. And I've got a video element that's actually playing the video. So what's different with this one, once we've set up the webcam, we're going to load the model. We then have a while true. Now that looks a bit weird because it's never going to terminate. A while true is going to carry on forever. But what we're doing inside this loop is at each frame of, or iteration of the loop, we're pulling a frame from the webcam, we're classifying that frame, and then doing a prediction. So you can see how quick it was actually doing it. It was doing it at like 30 or 40 classifications per second. So it is really fast. And one thing to note about MobileNet is it's actually designed for speed rather than accuracy, which is why it doesn't work so great in low light conditions. But I'll show you just now some ways that we can get around that. All right, so something else that I'm doing differently in this one is I'm checking the probability score. So we already looked at that earlier. And what I'm doing is making sure it's above some kind of a predefined value. Something like this is quite important to do, especially if you have something like a webcam that people could be in, because you may have a situation where you point it at somebody and it says they look like a safety pin and they could get really offended. And we already know that that doesn't really mean anything. It's a very low value. We're not even sure that they're a safety pin, so let's rather not print it out. So it's better in that case to maybe just print out we're not sure what it is, rather than printing out what the network might say.
So I was pretty confident that there were spiderwebs.
Pretty confident. Pretty confident, although this is only 0.3, so it's only 30% confidence.
Maybe it was picking up the cables in front of you.
Could have been.
Yeah.
It's a screen.
CRT screen, almost. Okay, so up until now, what we've been doing is feeding in an image where we're looking for one object inside the image. So we're assuming that that object takes up most of the space in that image. We're not doing anything to kind of like crop out the edges or remove things. So this is another model called Coco SSD, which is an acronym for stuff. Machine learning people love acronyms. And what this does is it looks for the location of various objects inside an image. So it's a little bit slower than the other one, which is why I haven't hooked it up to the webcam, because you'd get a very slow frame rate. But it essentially scans across the whole image looking for objects. When it finds the object, it tries to classify it, and it also gives you the bounding box of where that object is in the image. So what you could do is kind of pull out that bounding box of the image and put it through a different classifier and maybe get a slightly better prediction on what it is. Okay, I'm going to show you another one, and I want you to try and guess and see if you can tell me what it's doing. Might be easier to see if I point it at you guys. Okay, who can tell me what it's doing? Put your hands in the air. Okay, that doesn't work too well. So it's actually doing, yeah, Mike, come be a model. Like you just don't care. Cool. Thank you, Mike.
I hit my step goal, sorry.
All right, so this is actually doing pose detection, specifically human pose detection. If you point this at your dog, it's not going to give you any good results. But what it's doing is it's identifying certain key points on people. So it's finding people first of all, and then it's finding specifically, you can see the eyes, nose, ears, shoulders, as well as the arms and things. It's drawing lines between those different points. So let me show you the code for this. It's a little bit longer than our previous examples, but it's still not completely unmanageable. So we've got, you can see that it's about 60 lines of HTML and JavaScript. Importing tensorflow.js, our framework, we always need to have that. We're importing PoseNet, which is our model that's already been pre-trained. It's able to recognize these things. I've got a couple of helpers again just for drawing and setting up the webcam. I've got a video in Canvas for rendering the video element as well as drawing onto the canvas. And then I've got a whole lot of parameters. Now that might look quite scary, but these are all just the default parameters that I copy and pasted off of the implementation. Most of them are actually kind of self-explanatory. So you can see we've got max pose detections. That's the maximum number of people we'll be able to pick up inside an image. Obviously, the higher you make that number, the slower it's going to work. If you're intending to only point this at one person, you can set this 1, and then it won't pick up any other people that it might find in the background. Pretty much all of these parameters are a trade-off between speed and accuracy. So if you're working on an old mobile phone and you want to run something like this, you're going to focus more on speed. If you're working on a high-end laptop with an HD camera, you can focus more on accuracy. So once again, we're going to load up our model, posenet.load. And we're going to call this function detect poses in real time. And the important part of this is this model.estimate multiple poses. And that's where we pass in all of those parameters that we defined up at the top. That gives us back an array of poses because we're detecting multiple, so we'll have lots of them. And that'll give us quite a complicated data structure with all of the various key points in it, and that's what I'm drawing out onto the canvas. So what is something like this useful for? I mean, it's kind of cool to just stand in front of it and wave your hands, but what are you actually going to use it for? So things like this have been used for tracking performance of sportswomen. You can view your replays and see how you're performing certain actions in sport, and you can see where you're doing things wrong. But it also is kind of the basis for a lot of Snapchat filters. So for example, I made a quick little utility that'll put a hat on somebody's head. And it'll hopefully work on you. It's probably made a lot more money than a lot of other software people have worked on. A chip on your shoulder, that's also a really good idea. Okay, so these things are really great and fun to work with, but as we saw, there's only like 500 usable classes inside MobileNet, and it didn't really pick things up that well. And a library is only really useful if you can extend it. But we don't want to have to retrain stuff, because we don't want to have to go buy that $1,700 graphics card. So how can we extend these models without retraining them completely? What we can do is something called transfer learning, which is actually fairly new in the field of AI. And in order to explain that, I can close that. That worked. Okay. I'm going to have to dive into a little bit of theory, but we'll try not to get too technical. So this is quite a simplistic view of how a deep neural network works. And this is the underlying architecture of what's inside that model. On the far left-hand side, we've got something that we call an input layer, and that's got a number of nodes in it. And it'll have one node for each pixel in the image. So we'll convert each pixel into a numerical value, which will be the color of the pixel, and we'll feed it into the network. It'll go through a number of different hidden layers, and we'll eventually get to an output layer. During the hidden layers, there's lots of mathematical calculations and jargon that happens, but on the output layer, we will have one output node for each of the classes we're trying to identify. So MobileNet can distinguish between 1,000 different objects. There'll be 1,000 nodes in the output layer, and that'll give us 1,000 different numbers. All of those numbers will be a probability between 0 and 1 as to whether it's that item. So item number 26 might be a cat, 27 might be a ballpoint pen. We can look for the maximum in that list, the one that's closest to 1, and that's the probability that this thing is that particular object. So what we can see here is that it's only really the output layer that's classifying what object it is. All of the other layers are doing a bunch of other things, and until relatively recently, it wasn't really understood what they were doing. It was just kind of this magic black box that we throw stuff at, and we get results out at the end. But there's a very interesting paper where they actually figured out what those previous layers are doing. So some of the earlier layers are picking up edges, as you can see on the far left. They've got slightly different angles, but they're very fine textures. Then we start getting to slightly bigger textures, which are made up of a combination of different edges as we move through the layer. Then we start getting patterns, which is a combination of various textures. And then parts, when we get to parts, we're starting to maybe see things that we can almost recognize. We can see maybe there's like some flowers there, or fabric, eyes, something like that. And then we eventually get the objects that we're actually trying to recognize. So if we ignore the far right one, chop off the last layer of our neural network, we've already got a neural network that can recognize a bunch of different patterns. So what we can do is replace that last final layer with our own layer, and because it's already trained kind of like 99% of the way, it's really easy for us to add our own last layer and our own objects to train it. Let me see if I can show you an example quickly. Okay, so what I have here is a model and a new layer on the end that I've added on. And there's nothing in that layer yet. There's no node, so that's why it says nothing trained yet. What I'm going to train it with, I'll start with myself. I'm going to give it 10 to 15 training images. I'll move around a little bit so that it's got some variety. All right, and now it's predicting Richard for everything, because it's only got one item. So it's obviously going to predict that. So let's try give it something else. Didn't really get the mug earlier. Maybe I can get it now. Once again, 10 or 15 different things. And now immediately, we have a network that can tell the difference between me and a mug. I'll add a third one, just to prove that I'm not making this stuff up. Should be able to tell the difference between a Coke, me, and a mug. So this works really well because it's been trained in these lighting conditions. If I was to move to a place with different lighting conditions, it may change. But anyway, I wanted to take you through some of the important parts of that code, but I won't go through everything, otherwise we'll be here for a while. But it's also only about 60 lines of code. So it's nothing crazy. The main difference that we're doing is we've added on something called a KNN classifier. There's some more acronyms and jargon for you. That's K nearest neighbors, which is an algorithm that it uses. It's not important. You don't have to know what that does or what it means. But that's essentially the underlying model that we're using to replace our last layer. When we come to actually classifying our model, we're not going to call model.classify. We're instead going to say model.infer, which is a way for us to pull out the values from the second last layer. Second last layer happens to be named conv_preds. We're pulling out those values, and we're then predicting from our KNN classifier, which is the next line, using those values. So essentially what we're doing is we're saying each of these objects that I'm training is made up of a number of different combinations of textures from the previous layers. When we add a training example, we'll once again get hold of the values from the second last layer. We can add it to the classifier by saying classifier.addExample, and we'll pass through our activation and our class ID that we got. All right, so quite simple. I encourage you, if you're interested in this, to go read through the code. If you have any questions, you can reach out to me on Twitter, ZATech, Slack, anything like that. But it's pretty easy to build something like this, and it's really impressive to show your coworkers and your friends, because you can train it on pretty much anything and just get it to recognize a bunch of stuff. So one thing to just remember about this is we're using MobileNet. And like I said, MobileNet has been trained on largely animals and common household objects. So you can't really use this for images that don't fit into that category. So things like satellite images and X-ray images, it's probably not going to do so well, because those first couple of layers where it's picking up those textures are going to be different for different classes of images. So as long as you're just recognizing objects, this should be pretty easy. Okay, so the examples from this talk are available on my GitHub profile. A list of all of the TensorFlow.js models is available on the TensorFlow GitHub. There's about 8 of them. There's some pretty cool ones, including ones to try and detect intent in written text. So try and figure out if somebody is being mean or not. There's a really interesting blog post called Machine Learning for Everyone, which kind of gets through all of the jargon and really targets people that are interested in learning a lot, but not interested in learning all of the math and complicated stuff that you don't need to learn. And then there's an interesting library called ML5.js, which is actually built on top of TensorFlow.js. What they try to do is they try to make it a little bit more human accessible and human readable to work with TensorFlow.js. For simple examples, though, you'll see the code will look pretty much the same as what I had here. But if you want to do something a little bit more complicated, that might be a really good thing to look at. Cool, that's me. Any questions? Yeah.
My question is more on the user side. The network speeds are not exactly the best in South Africa right now. So how much of an impact does that have when someone is using it to still see or...
So it depends a lot on what model you download. Some models are a lot bigger than others. That PoseNet model is a really good one. I think it's only like 3 or 4 megabytes big, which in terms of web is quite a lot, but if you look at what it's doing, it's performing really well. ImageNet is quite big. I think it's more than 10 megabytes big. So you need to build that into your user experience. Make sure the user knows. I mean, first of all, like if they're on very slow internet, they're going to see your application hanging while it's busy downloading this thing. But maybe let them know that when they click onto this thing, it's going to download the model. Or a lot of example websites have a separate button that allows you to click download model, tells you how many megs it is, and once it's downloaded, then you can actually start using it. But it depends a lot on what model you're using.
So, just you can persist your models over sessions and stuff like that if you want. So.
Yes, so I didn't show any of that code, but it is possible to actually save those weights. And you can save it in local storage. You can save it as a file that you download. you can either upload it to the server if you want to. If you want to create like a utility page or something that allows you to train it, then save it to the server and then have that served to anyone else that views it.
So then theoretically you can have like that in a flow that you can train and then you submit it to like a central server where you can have like 5,000 or 6,000 users.
Yeah. Something else that's quite important is you can take any of the normal TensorFlow models that have been trained using Python and convert them to JavaScript as well. And that's actually why most of the models are still quite big, is because everyone works in Python because it's really easy to run on a bunch of GPUs, and they don't really care how big the model is. So no one's done any kind of optimization to make the models really small.
So does TensorFlow do that automatically? Or?
I mean, you have to code it, but it's kind of like, it's a library where you just say convert to tensorflow.js. There's also a couple of open formats. I think ONXX is one, which is somebody's trying to make a general standard for models that you can import to any library.